Hello, today we are going to be taking a look at kinetic molecular theory of gases, and then we also are going to be talking about kinetic energy, velocity, and the Maxwell-Boltzmann distribution, which has to do with velocity of gases at different temperatures and different gases. So first off, kinetic molecular theory, we did cover this in Regents chemistry. And what that states is that gases are composed of molecules that are separated from each other by large distances. So as you can see, our gas molecules are very wide apart. They are spread very far apart. So they consider the individual molecules to have a negligible volume. So that's one of our key points of the kinetic molecular theory is that the individual particles, while they do have mass, have a negligible volume. And again, the way that that is justified, because obviously they do have volume because they do exist, they do take up some space, but those individual particles are so small compared to the container as a whole that those individual particles make up a negligible amount of the total volume. All right, our second thing is that the molecules are in constant random motion. So they move in a straight line until they hit something, be it the walls of the container or another particle, and then they bounce off in another straight line. It's random motion, so they're not attracted to one area over another. And the collisions between the molecules would be perfectly elastic, meaning that there can be a transfer of energy, but there is no loss of energy. Gas particles are, in order to be perfectly ideal, are not supposed to have any attractive forces or repulsive forces between them. So if you have a perfectly ideal gas, there should be no intermolecular forces. And obviously that is not totally true, but gases do have weak intermolecular forces, which is why they exist as gases. So for a lot of our gases, this is close enough where our gases can be considered close enough to be ideal. But to be perfectly ideal, they should have no intermolecular forces. So the ones that have weaker intermolecular forces are going to be more ideal. Stronger intermolecular forces would be less ideal. And then our last point is that the average kinetic energy of the molecules is proportional to the temperature, and that's going to be in Kelvin because all of our gas law calculations have to be done in Kelvin. And if I have two different gases, if they are at the same temperature, they will have the same average kinetic energy. Now remember that is average kinetic energy because some of the particles are going to be moving with more or less kinetic energy. So same temperature, same average kinetic energy. So some things that I just want to review. If I increase the volume at constant temperature, then the gas particles are going to spread out more. So there would be fewer collisions with the walls of the container. So therefore, we would see a decrease in pressure. Now, if we increase the temperature while keeping the same volume, the particles are going to start moving around more. They're going to have a greater average kinetic energy. So therefore, the pressure will increase because there will be more collisions with the sides of the container. And since they have more kinetic energy, those collisions would be more forceful too. So we would see an increase in pressure if we heat up the gas. All right, now we need to talk a little bit about kinetic energy and speed or velocity. So if I have two different gases and they are at the same temperature, they will have the same average kinetic energy. As we talked about on the previous slide, that's average kinetic energy because some particles will be traveling with a higher velocity. and some will be moving with a lower velocity. So again, average kinetic energy. So those of you that have already taken physics or are currently in physics should recognize this formula. Kinetic energy equals 1/2 mv squared, where m is mass and v is velocity, which would be measured in meters per second. So if we are at the same temperature, they will have the same kinetic energy. But if your two different samples have different masses, they will have different velocities. So if they're at the same temperature, they will have the same kinetic energy, but they will not have the same velocity. So, because it's 1/2 mass times volume squared. So the result, the kinetic energy will be the same if they're at the same temperature, same average kinetic energy, but their velocities will be different if they have different masses. So if we are at the same temperature, if we have less massive molecules, like let's say helium versus carbon dioxide. So if we have a sample of helium, sample of carbon dioxide, they are both at the same temperature. The helium is going to have less mass, therefore it would have to have a higher velocity than the carbon dioxide would in order to get to the same kinetic energy. All right, now we have these graphs that you're going to see very commonly, and you might even recognize them from COVID. It's the flattening of the curve. We'll talk about that in a second. So the Maxwell-Boltzmann distribution shows us that the temperature of a gas is a measure of the average kinetic energy of its molecules. We already know that. And again, that does not seem that every molecule has the same exact speed. Some will be moving faster, some will be moving slower, hence average kinetic energy. But we know that if we are at a higher temperature, more of those molecules will be traveling at a higher velocity, thus registering a higher kinetic energy. So that is what we see on this graph here. So this graph has the same gas. So this is all the same gas. So let's say this is nitrogen gas. So this is nitrogen gas. So each one of those three samples is nitrogen gas, but at a different temperature. So what we can see is when we are at 100 Kelvin, this is the average speed here. So the average speed at 100 is lower. If we take our same sample, but heat it up to 300 Kelvin, we know that on average, more molecules will be moving faster. Not every single molecule, but more molecules will be moving faster. So at 300 Kelvin, this is my average. So again, I want to look down. My average would be, around maybe 400 meters per second. So at 700, here we go, 700. Here is my average. On average, this is the average molecular speed. So the graph gets flatter at a higher temperature. So like I said, kind of looks like the COVID graph and flattening the curve. So you're pushing that curve down. You still have the same area under the curve because we still have the same sample. So if we have 1,000 molecules, underneath all three of these curves, we still have 1,000 molecules. As we heat up our sample, we get that flatter curve, but on average, the molecules are moving faster and you do have more fluctuation. So there's more variation in their speeds the higher the temperature goes. So same area underneath the curve, you want to look to see where that middle of the curve is. So that average molecule is moving faster at a higher temperature. Now we have a very similar curve for three different gases, all at the same temperature. So we have 3 different gases here, and they are all at 300 Kelvin. We have Cl2, N2, and helium. So Cl2 is our heaviest of those 3 gases, so we would anticipate it moving the slowest, because if they're all at the same temperature, they will all have the same average kinetic energy. But since kinetic energy is 1/2 mv squared, if Cl2 has a higher mass, it will have a lower velocity. So on average, Cl2's speed is there. Okay, N2 is lighter than Cl2, but heavier than helium. So it's going to have a speed that would be between them in the middle. So again, you want to look to see where the peak of the curve is, and then that would give you your average speed. Helium is the lightest out of these 3 gases, so we would anticipate it having the highest velocity. And we can see, here's the middle of the curve. If we go down, it would have a velocity greater than 1,000 meters per second. So again, what you want to do, find your middle point, go down, that would give you the average speed for those molecules. The height changes because the curve flattens out at a higher temperature. So at a higher temperature, you still have a higher average velocity, but there is more variation between the molecules. So some will be moving faster, some will be moving slower. But if they are at the same temperature, they will have the same average kinetic energy, but that does not mean that they will have the same velocity. So higher mass, lower velocity, smaller mass, higher velocity. All right, so this gives us an example problem, and you don't have this in your notes, but that's fine. We can follow along with it. So we have this original diagram. That original diagram shows us N2. And then they want to know which one of these 4 choices down here, 1, 2, 3, 4, would show us O2 in relation to the N2. They are both at 25 degrees Celsius, so they both have the same temperature. So same average kinetic energy, but a different velocity due to a different mass. So N2 would have a mass of 28 grams per mole. O2 would have a mass of 32 grams per mole. O2 is heavier, therefore O2 should have a lower average speed. So O2 heavier, therefore lower average speed. So we are looking for where the dashed line correlates to a lower average speed. That is going to be this first graph here, because O2 is the dashed line, middle, down, that would be a lower average speed than nitrogen's would be. So this one showing a higher average speed. This one also is showing a higher average speed. And graph B is just kind of weird looking. That's not how it changes. It at a higher speed, there's more variation. So that's why N2 is a little bit flatter of a curve than O2 is. But again, you just want to find that average spot on there.